All right.
But we're not going to dinner.
And OK, so this is the outline of the talk. So Juan asked me to give a review of a project I worked on with Andy Knightsky and David Gaiato, starting here at the Institute for Advanced Study, from around 2008 to 2012. So that's with David Gaiato and Andy Knightsky. And well, that's 6 papers. That was about 739 pages. And then there was a tiny little follow-up with David Gaiato and Edward Witten. That's another 475 pages. And well, nobody wants to read all that. And allegedly, there's some results in all those pages. So I'm going to sketch for you a few of those results. Now, when Juan asked me to give a review talk about GMN, and so I asked Juan, well, do you want a particular subject stressed? This was years ago. Why do you want to hear about this? Do you want cluster coordinates because there are amplitudes people interested? No. I want. So after some back and forth, exactly what Juan wanted. Just a broad, superficial overview of those papers. By the way, I'm not going to be there. So if this is not what you want, well, go blame Juan. So for these papers, some of the keywords are here. So 4-dimensional n equals 2 field theory, BPS spectrum, Wallcrossing, hyperkahler geometry, holomorphic vector bundle, Stokes phenomenon, and on and on and on. And if you're not interested in any single term on that blackboard, then why are you here? So OK, so the project starts with 4-dimensional n equals 2 BPS states and their Wallcrossing. So let me bring Coles to Newcastle and talk a little bit, a quick review of 4-dimensional n equals 2 field theory. So we have a 4-dimensional, a unitary quantum field theory, and it has some a Z2 grading on the Hilbert space, and there's some odd operators, and there's supersymmetry operators, and the notation here is quite standard. So I'll just write down the superalgebra, and if you need notation defined, just holler. So we've got this algebra of operators, and then Q alpha I with Q beta J is the invariant symbol on the Weil spinor indices. Alpha beta goes from 1 to 2, and the invariant tensor on the SU2R symmetry indices, I and J goes from 1 to 2. And then there's a central charge, and it's a good convention to put the bar there. OK, so if there's any notation that you need, explain, just ask me. It's all very standard. So OK, so inside the Hilbert space of all states, there's a subspace called the BPS space, which are those quantum states such that the Hamiltonian on those states is the absolute value of the central charge acting on those states. And I think that's a concept that certainly goes back to Olive and Witten, 1977 or 78. And I think the term BPS state was invented by Zyberg and Witten in 94. Because it played an important role in their work, as we'll soon see. Now, so these theories have a moduli space, a vacua on 4-dimensional Minkowski space, which is a little unusual for quantum field theories. There's a whole space of possible Lorentz invariant vacua, and it has many components, not exactly connected components, but because they're connected, but subspaces. The Higgs branches, and we're going to be concerned with the Coulomb branch. where, rather importantly, there's an unbroken abelian gauge symmetry. So this talk is completely focused on the Coulomb branch. Because there's an unbroken abelian gauge symmetry, there are abelian gauge fields in the low energy theory. And because we have unbroken n equals 2 supersymmetry, we have to have U1 vector multiplets. So remember what that looks like. So you have a photon, a mu, and then you have two photinos, 2 because you have n equals 2, and they're a doublet under SU2R. And then there's a complex scalar field, phi, and that phi takes a vacuum expectation value, and that's how you're going to describe your vacuum. You can get a real workout here. Moving these boards around. So if we have U1 to the R unbroken symmetry, that's our abelian gauge symmetry, then we have an R complex dimensional space of vacua. That is M Coulomb. All right. So now there are two basic problems you can think about. It's okay, Lisa, I got a copy. Thanks. There are two basic problems you can think about. Problem one is describe the low energy effective theory on M Coulomb. So you choose a vacuum on this Coulomb branch and you ask what is the low energy effective theory. And problem two is describe the BPS states or the BPS spectrum. Okay, so here, the answer to problem one is the Seiberg-Witten paper from '94 plus approximately 10 to the 4th follow-up papers. And I'll explain a little bit what the solution looks like. And the answer here, so this is a solution for a large class of theories, a very large class of theories. Although as far as I'm aware, we don't have a solution for an arbitrary n equals 2 theory. If I give you an arbitrary n equals 2 Lagrangian, can you tell me the low energy effective theory? I'm not completely sure we know the answer to that. Now here, as I'll maybe get to at the end, GMN solves this question for a large class, but much smaller than this class, for what are called class S theories, which includes many of the normal theories you would tend to write down, like n equals 2 super Yang-Mills. Okay, so what does the solution to the low energy effective theory look like? Well, so we've got this Coulomb branch. Yeah, let me put it over here. We've got this Coulomb branch. So it's an R complex dimensional manifold. I'm also going to call it B. B is just, I'm changing notation on you. And a generic point in B I'll call U. And so at this vacuum U, we have an unbroken electromagnetic abelian gauge symmetry. And so we have a lattice. So above this point sits a lattice, gamma sub U, which is the lattice of electric and magnetic charges. Now, there's no invariant distinction between electric and magnetic charges because of duality, but we could make a choice, and then we have a lattice of electric and magnetic charges. And then there are points on this, well, not points, but codimension 2 subvarieties, where there are new massless BPS states. So the spectrum of the Hamiltonian varies as we move around the Coulomb branch, And in particular, the space of BPS states varies as we move around the Coulomb branch. And then there are codimension 2, real codimension 2, complex codimension 1 subvarieties where massless, there are new states which become massless. So I'll call that B singular. And so this lattice of charges is a bundle over B star, which is B minus B singular. And it has monodromy. So it's not a trivial system of lattices. And another piece of structure we have is an integral antisymmetric pairing. So this is Z valued and antisymmetric. And so this is just the DSZ pairing on electromagnetic charges. So then as a representation of the n equals 2 superalgebra, the Hilbert space depends on U. And because of the abelian gauge symmetry, it's graded by charge sectors. And now there's a nice fact. I don't know an a priori proof of this, but in the models I understand, it's just a fact that if you restrict the central charge operator to an electromagnetic charge sector, then this is proportional to the unit operator. And the proportionality constant is a complex number, which depends on gamma and U. That's the n equals 2 central charge. And this will be useful later, it's linear in the electromagnetic charge. All right, so you have those structures, just given n equals 2, d equals 4. And now a non-obvious but true fact, which comes from the structure of n equals 2 supersymmetry, is that the functions z gamma completely determine the low energy effective action through something called the prepotential. So if you know the functions z gamma, then you can get the prepotential, and from the prepotential you write the Lagrangian in a very straightforward way. Okay, so what does it mean to solve problem 1? It means you give some way of writing down these functions z gamma, and that's what Seiberg did. So there exists a holomorphic family for this class of theories where we know the solution. There exists a holomorphic family, sigma u, called the Seiberg-Witten curve, and lambda u, a meromorphic one form on sigma u, called the Seiberg-Witten differential. And they vary holomorphically with u, such that gamma sub u is equal to the first homology of this Riemann surface. Well, okay, already here I'm telling you a lie, so I'm going to put in the Bourbaki danger sign. So it might be a sublattice or a subquotient, but essentially it's the first homology. And well, indeed, the first homology of a Riemann surface has an integral antisymmetric form on it, right? You can just take the intersection of the curves on the Riemann surface. And now, because you specified this data, the formula for z gamma of u is just the periods of lambda u around gamma. And so I just told you, if you know those functions, then you know the low energy effective action through a formula I'm not explaining to you, but it's quite standard. So this is the solution. So the solution is you find a suitable family of holomorphic family of Riemann surfaces with one forms, and you're all set. Now, I don't know, when I said for a large class, not for all theories, I actually don't know of a general construction given a four-dimensional n equals 2 Lagrangian, how to construct automatically the Seiberg-Witten curve and the Seiberg-Witten differential. I don't know if there's any procedure. There even have been papers, I don't agree with them, but there have been papers claiming that there are four-dimensional n equals 2 theories where there isn't a Seiberg-Witten curve. Anyway, so I think that's an interesting problem to find a general procedure.
These papers claim there's a family of abelian varieties, but you can't derive it from the curve.
Well, you always get it automatically a family of a billion varieties. So then you then you say, okay, is that a Jacobian or a prim? And then you need to find a suitable one form. So Coulomb wrote a paper using some geometric engineering story that claimed that there was no Seiberg-Witten curve. And there might not be a natural one, I don't know. Okay, so what about problem 2? Okay, so in problem 2, so we have, as a representation of the n equals 2 algebra, we have our Hilbert space is graded. Inside here is the BPS space, which will depend on you, and it's also graded. So, okay, so this is the problem. So we want to give an explicit, or as explicit, a construction of these spaces as we can, or at least say something about the dimension. When are these, or even a cruder question, which is still a hard question, is when are these spaces 0 and when are they not 0? So that brings me to the topic of Wallcrossing. All right, so even the dimension of H BPS gamma U can jump discontinuously as a function of U. And there are at least 2 reasons for that. One is the more prosaic reason that hypermultiplets and vector multiplets, short representations of the superalgebra, can pair up to a long representation. And the less prosaic reason is Wallcrossing. Okay, so let's deal with the prosaic reason. One way to deal with it is study an index instead. So the index is then blind to this kind of pairing up. And the explicit index that you study is omega of gamma, y, and u, which is by definition 1 over y minus y inverse, the trace over this BPS space of 2j3 minus 1 to the 2j3. It's essentially a Witten index. There we go. So J3 is a rotation generator for rotations in space. Remember, we're talking about a particle that's sitting there in R3. So we have rotations around that point where the particle sits. And then I3 is a generator of the SU2R symmetry. And a little bit of indexology shows you that this y minus y inverse cancels out of the Laurent polynomial that you get from taking this trace. And what remains is actually a character of a spin representation. So the reason for this here and this here has to do with the factoring out the center of mass motion of the particle. So this is an index. Indeed, in some cases, it's literally the index of a Dirac operator. And so therefore, being an index, you don't expect it to change. But that's the surprise of Wallcrossing. So the surprise of Wallcrossing is that it's piecewise continuous. Okay, it's basically an integer quantity. It's a character of some representation, so that's a rigid thing. So it should be constant, but it's only piecewise constant. That's Wallcrossing. And why is there Wallcrossing? Well, physically, there's Wallcrossing because BPS particles can form bound states which are themselves BPS. And so that goes back to Cicciotti and Trilligator Vafa, and Cicciotti, Fendley, and Trilligator and Vafa, and Cicciotti and Vafa in 92, and again was very important in the story from Zyberg and Witten in 94. And so there's a nice physical mechanism for thinking about why there's a wall crossing. So you take two of these BPS particles of charges gamma 1 and gamma 2, and then using some nice techniques, Frederick Deneff derived in a semi-classical approximation a formula for the bound state radius. And it involves something like gamma 1, gamma 2, divided by, importantly, the imaginary part of z gamma 1, z gamma 2 inverse. So this, you see, now goes to infinity when this imaginary part vanishes. So here is the Coulomb branch. And so there's a marginal stability wall, ms of gamma 1, gamma 2. So given a pair of charges, you can define a wall where z of gamma 1 is parallel to z of gamma 2.
This
Yep.
R1, 2, what exactly is it?
It's in supergravity, or also in the field theory limit. You have these bound states, these BPS bound states. So originally it was derived for BPS black hole solutions, multi-center black hole solutions, and there are two centers of the black holes, and this is the bound state radius. Okay, and you can also take a field theory limit of that.
If the theory is strongly coupled, if you have a classical solution for,
Yep.
for some diode,
Yep.
then I can understand your estimates. But if the theory is strongly coupled, how exactly do you define R1, 2?
You would actually have to work with wave functions. So in fact, I've done that. Again, in the semi-classical approximation, where I can write wave functions on the monopole moduli space, and I can study the bound state wave functions, and I can see that they peak. And okay, so semi-classically, so this is a classical picture, really. Frederick's supersymmetric black hole solutions are classical solutions of n equals 2 supergravity, but it works extremely well, and it gives a picture which seems to work extremely well for deriving wall-crossing formulas. So my feeling is that this is actually, even in a strongly coupled theory, if I'm going close to a wall of marginal stability where this radius is very large, you see, I could imagine one of these is very heavy and one of these is very light, and study this as a probe particle.
Why does it matter? Why do you want to be like, once R1, 2 is big, that's the discussion.
That might be right. So maybe I'm being unnecessarily restrictive. But once R1, 2 is very large, then I think the semi-classical picture should be good. And the whole point of this is that R1, 2 will be large, very close to a wall of marginal stability.
The question was, I see the intuitive picture.
Yep. Mm-hmm.
That's clear to me. It's clearly valid given the strong coupling. But how do you define R1, 2?
You only have to define what it's big.
Yeah, exactly.
But even when it's big, it's not too.
No. Then if it's big, if I have a semi-classical approximation, I look at the support of the wave function.
It's not.
And as I said, you can literally do that using the collective coordinate, wave functions on the collective
This
coordinate
is
space.
useful if we coupling.
We don't need to define R1, 2 exactly.
We just need to define it in an infinitesimal neighborhood of the wall of marginal stability.
Exactly. What we're trying to say is that there's a two-particle downside on one side, these sides divergence.
Absolutely. That's all I'm trying to say. And yeah, so I'm just trying to give you an intuitive picture here.
Then there's an explicit formula.
Yep.
Specifically, there's no pi out front or something.
It hasn't really.
Well, actually, I just wrote R1, 2 goes to infinity here. And literally, I'm doing this from memory. And I think there might be a factor of 2, and there might actually be a z of gamma 1, z of gamma 2. But okay, but there's some factors here. Yeah, that's the crucial point. That's all I'm trying. That's okay. We shouldn't get hung up on this. The idea is that you can form bound states which dissolve across the wall of marginal stability, where this is true. And I believe that this is a good picture, infinitesimally close to the wall of marginal stability. And this kind of semi-classical reasoning actually works extremely well.
Is it clear that it's really inversely proportional to the imaginary can there be, say, a critical exponent there, which is not exactly one?
Oh, well, I mean, it would have to, I don't know.
What if there's an additive uncertainty from the size of the particle?
Yeah, I mean, it would have to be some function of u which goes to 1 as u goes to infinity. As u goes close to the wall of marginal stability. It should be universal for pairs of charges. Okay.
Isn't this just deduced from the long-range forces between the particles?
Yeah, that's the probe. Yeah, that's what I was starting to say about the probe. So you treat one of these as a probe in an effective action created by the other particle. You write down its Lagrangian and you look at the minimum of its potential energy, and this is where the minimum is. Okay, we really should not get hung up on this. I mean, there's more to say, but you guys look really unhappy. But
The only thing I'm unhappy about is that you're relying on the probe approximation, which I think is unnecessary. It's like Jupiter. We have 2 planets. If they're far enough apart,
I think you're probably right. All I'm saying is that one way of deriving it that I'm quite certain about, because I've gone through all the details, is in the probe approximation, where I take this as creating a background for this and study the superquantum mechanics of this collective coordinates, and then this distance is one of the fields in that superquantum mechanics. It has potential energy, and that potential energy has a zero right here. Okay. Okay. So after all that, you're not going to believe what I say next. But so using this picture, you can say how this index actually jumps. These are the bound states that you lose as you cross this wall. So what's the change in the index? Well, it's going to be the index for the degrees of freedom of this particle times the index for the degrees of freedom of this particle. And then these are dions. So you know that if you have a pair of dions, we have an electric field here and a magnetic field from here, and they form some angular momentum. And so when you quantize that angular momentum, you get some other degrees of freedom. So you get the character of spin j, where you work out j is just essentially the inner product of gamma 1 with gamma 2, and the exact formula is that. Okay, so this is called the primitive Wallcrossing formula. And it was written by Frederic Deneff and myself in 2006. And it doesn't apply if gamma 1 and gamma 2 are not primitive. So it's only valid for gamma 1 and gamma 2 primitive. Primitive means it's a vector which you cannot divide by an integer and still get an integer vector. And why? Well, if you take 2 gamma 1 and gamma 2, for example, you could have more complicated bound states, even in this classical picture. And for general charges, which are not necessarily primitive, you need a much more complicated formula called the Kontsevich-Soiberman-Wallcrossing formula, 2007. And I'm going to give a physical derivation of this Kontsevich-Soiberman-Wallcrossing formula. So if I tried to explain what it is as a mathematical statement, you'd all fall asleep pretty fast. So, but I hope you'll see that it's very natural physically. Now, this is where my project with Andy and Davida started, to give a field theory derivation of this KS Wallcrossing formula. And to do that, it's not our original argument, but the best argument relies on defects. So now I want to move on to defects and their BPS states. Okay, so the first one we want to look at are line defects. So these are codimension equals 3 defects in 4 dimensions. And as opposed to what people are doing in condensed matter physics, we're going to take some very special ones that preserve 1/2, that is 4/8 of the supersymmetry. And we have to say what four-dimensional subspace of the 8-dimensional space of all the supercharges we take, and that implies that you need to make a choice of phase zeta. So there's some families of four-dimensional families of supersymmetries that are preserved by these line defects, and they depend on a choice of phase zeta. So for example, in super Yang-Mills, you would write the supersymmetric Wilson line operator. It would look something like this. Zeta inverse phi plus A plus zeta phi bar. And you would put this at a point times time, which will soon be the Euclidean time. Okay, so that's the kind of line defect I'm talking about. That's an example. Now, in the presence of a line defect, well, it's sitting at a point and it's modifying the Hilbert space. So I'll call H sub L the Hilbert space in the presence of the line defect, and it's still graded by a lattice, or more precisely, by a torsor for a lattice. There's a shift. So in this subject, shift happens. And here, the BPS bound is modified. So in charge sector of the Hilbert space in the presence of the line defect, the energy is bigger than or equal to minus real part of zeta inverse z gamma L. Okay? So this is the new BPS bound. And accordingly, we have new BPS states. These are called framed BPS states in the presence. So framed BPS states are BPS states that saturate this bound. Yes?
Are the quantum numbers of these gamma such that they do not exist as particles in the spectrum or not?
They might not, yeah. So because of this shift, you might easily, this shift is like a fractional lattice vector. And so typically,
in SU2, this could be the fundamental.
Abs-
The Q gauge SU2 is the fundamental one.
yeah, for example, you can have that kind of
There's
thing.
only one non-trivial there. Only one non-trivial.
Yeah, I mean, for example, with the Tuft operators, that's another good example. You can put in a Tuft operators using a co-character that's not a co-character of the actual
So specifically in SU2, you don't have, there's only
group
one
that you have.
non-trivial defect in this definition. Because everything else can.
Oh, no. There's only one non-trivial S sub L. But the defect, I could still,
That's in the same.
the defect is like an infinitely heavy particle.
Yeah, but that's in the same Hilbert space.
If you think an infinitely heavy particle is in the same Hilbert space.
Quantum numbers that exist.
It has quantum numbers, but it's not actually a state.
The defect is a line operator, so it could exist in any dimension.
Right, absolutely, yeah.
So in particular, SL can be zero.
SL could be zero. SL could be zero.
But then in that Hilbert space, the regular vacuum is also there, because I can bring from very far particles.
No, because this defect sort of shifts the energy by infinity. So this H, I don't think you can, this H sub L, I mean, just look at the BPS bound.
Well, that's exactly why I asked the question.
The BPS bound is different.
Is this energy or energy? This is energy.
This is the energy.
So what stopped me from bringing a particle from very far,
Yeah.
sticking there and bringing everything to, making it trivial?
Because that particle, what you can do is you can couple that particle to another flavor symmetry and take the weak coupling limit of that, make it a monopole for that other flavor symmetry, take the weak coupling of that and make its mass go to infinity. But you've got to have a defect.
And so let's discuss the SU2 problem, just pure
Mhm.
SU2.
Mhm.
There's no flavor.
I could have introduced a flavor. It's your trick. I could have introduced some extra symmetry, weakly coupled to that extra symmetry. So I'm simply discussing, so I insert this into the path integral. It's going to change the spectrum of the Hamiltonian. Look, it's going to change the equations of motion. Another example are Tuft operators. What am I doing then? I'm making the field singular as I go to x equals 0. That's again going to change the spectrum of the Hamiltonian. So it's a very important point. These framed BPS states are really not the same as ordinary BPS states.
As you said, they would be ordinary BPS states in a different field with a very heavy flavor.
Yeah, that's a good way to think about it. Yeah, absolutely. So one way of making these line defects is exactly that. You have some extra U1 or something. You take a monopole for that extra U1 coupled to some quantum numbers in the field, in the theory you're interested in, and take the weak coupling limit of that extra U1. And so then it's becoming infinitely massive, and it's acting like a line defect. OK? All right. So framed BPS states saturate this bound. Now, because of the change of room, I had to get myself all prepared in a hurry twice, and I forgot to set my alarm clock. So let's see. So I've got till 2:20. Let me set my alarm clock right now. And while I'm doing it, are there any questions?
Yeah, quick question about Wallcrossing.
Yeah.
How do you tell from that formula which way the index is jumping if you go from one side to the other?
Right, good. So the point is that the point is that we're assuming when I write this formula that there exists a bound state on one side and there's no bound state on the other side. Okay? And so, yeah, so you do have to be careful about which, in Wallcrossing formulae, you definitely have to be very careful about which way you're going across the wall. Now, because this is a quick overview, I have chosen not to be extremely careful about that kind of detail. But it's done very carefully in the papers.
In general, there'll be more than one such BPS state, right, on either side, and so you're asking. So maybe some combination of them will.
Well, I mean, there's a space of BPS states. There's a space of BPS states of charges gamma 1 plus gamma 2. Maybe what you're saying is this could be decomposed in terms of a sum of charges, positive charges, in other ways. That's true. That's true. I'm describing one kind of decay. All right, so framed BPS states, so where was I? So framed BPS, so framed BPS states saturate this bound, and so we can define a framed index. So it depends on a lot of data. It depends on the line defect, in particular the phase associated with the line defect, the charge. I guess I should call that gamma L, Y, and U. OK, so this is by definition H sub L sub BPS gamma U, gamma LU, minus 1 to the 2J3. It's again a Witten index, minus Y to the 2J3 plus 2I3. And because the line defect is broken, the translation symmetry, we don't have all this nonsense with the insertion of 2J3. OK, so these also have Wallcrossing. And as functions of U and zeta. And where are they crossing? Well, the analog of marginal stability walls are what we call K walls or BPS walls. And so they're the set of U and zeta such that zeta inverse Z gamma is less than 0. You'll see why in a moment. So this is, we often call this a K wall for reasons that I'll explain later. I hope I get to it. And just like over here, when you're close to the wall of marginal stability, when you're close to a K wall, there's a very nice semi-classical picture of exactly the states that you're losing, which account for the Wallcrossing of omega bar. And so it looks like this. So you have some, at the location of the line defect, you have some state of charge psi gamma C. The C is for core. And then you have what we call a halo. So out on this halo, you can insert 4-dimensional ordinary BPS particles of charge gamma or 2 gamma or n gamma. And these are all BPS, so they're mutually non-interacting with each other. And so you can insert as many of them as you like. And there is, again, by a probe approximation calculation, a formula for the bound state radius, which, again, you can verify with Dirac operators on monopole moduli spaces, which looks like this. And so, again, this bound state radius, this halo radius, goes to infinity as you cross one of these walls. So the difference is that what you lose are entire Fock spaces, because you can have a whole Fock space of particles of charge gamma, 2 gamma, 3 gamma, and so on, all inserted on this, this spherical shell. So what happens is Fock spaces come and go in these spaces of framed BPS states. Now, to answer your question, Nadi, again, or to come back to the issue you raised, there could be all sorts of complicated states in here. That's some kind of strong coupling phenomenon. We have nothing to say about that. We're just talking about the states that come and go as we cross these walls. So all we need is that this picture is valid in an infinitesimal region of this wall. All right, so that's line defects. Question? Yes?
The formula for the radius
Yep.
only tells you that you basically lose the bound space when imaginary part is 0. But the definition of the K-wall is like a real part being negative.
Are you worried about the sign? Yes. That's related to the other question. So if you're really careful about the states that come and go, it's actually negative and not just real. Yes, it's a good point. And again, that is addressed very carefully in the papers. But I'm running low on time, and I haven't even gotten to the really important stuff. So, so the other kind of defects you can write are surface defects. And to explain what's going on there, let's start, before talking about the 4-dimensional theory, let's start with 2-dimensional, n equals 2, 2. And to fix ideas, quantum field theory, and to fix ideas, you might want to think of a Landau-Ginzburg model for a Kähler manifold target, Kähler target X and a superpotential W. And so then there are going to be massive vacua. I'll label them I, J, K. And these are just the critical points of W. And so then famously, these theories have BPS solitons, where we have boundary conditions. This is a picture of the spatial X line, where my 1 plus 1-dimensional quantum field theory lives. And so there are vacua I and J on either side. And we have I not equal to J. And well, in this soliton sector, there's a central charge, which is the difference of the critical values of the superpotential. And you have BPS solitons. And there's an index, which is, again, a Witten index. J is the U1 charge. And that's there for the center of mass. And so again, there's Wallcrossing, as discovered by the people I mentioned before. So the walls of marginal stability are labeled by IJ and JK. That's a comma there, and a JK, which is inside, let's say, the space of W's, space of parameters of the model. And it would be equal to the space of superpotentials such that Zij is parallel to Zjk. Very much like the wall definition of the wall of marginal stability up there. And as you cross that wall, an IJ soliton breaks apart into a bound state of say an IK soliton breaks apart into an IJ and JK soliton. And so as you cross this wall of marginal stability for IJ, comma JK, what happens is one of these indices changes. And this is what Cicciotti and Vaffa wrote in '92. And nowadays we understand it as a very special case of the Kontsevich-Soibelman formula. Well, now suppose that we have this 2D theory now with a global symmetry G. And for simplicity, let's say G is a continuous Lie group. And then we can embed this 1 plus 1 dimensions into 4 dimensions, say along the plane where y and z are 0. So this is now, imagine this sitting inside 3 plus 1 dimensional Minkowski space. And we put our 1 plus 1 dimensional theory here, and we couple it to an ambient 4-dimensional G super Yang-Mills, or n equals 2 theory with G gauge symmetry. And then we get what we call a 2D 4D system. And that implies new phenomena. One of the main new phenomena that we can get is we can have new kinds of BPS solitons that look like this. We have the same vacuum, I here and I here, and a 4D BPS particle has bound to this line, the surface defect. In fact, we argue in our paper that it's good to think of this surface defect as a kind of solenoid that can carry fluxes of the 4-dimensional abelian gauge theory. And so if we have this gamma here, we have new 4-dimensional BPS degeneracies that depend on gamma and also the differences of the fluxes. So now there's a 4D a Wallcrossing formula, generalizing Kontsevich-Zweibelman, which mixes the mu's and the omegas. And now the other thing you can do with surface with defects is you can, of course, have defects within defects. Yep.
In the top board, is the problem purely in 2 dimensions?
In the top board, I am working purely in 2 dimensions.
There, the states is dissolved.
So until this point, yeah. Until this point, I've been working in 2 dimensions. And now, that was just to get you warmed up, to couple it to a 4-dimensional theory.
Right, so in the top board, the phenomenon is a bound state splits.
Yep.
And at the bottom is that something can escape to the bulk.
Well, we can have different, well, this is much more complicated. So
Split inside.
so you could split inside, you can have a 4-dimensional bound state, a 4-dimensional particle gets trapped. And so this formula is necessarily much more complicated, but we wrote it. And now you can also do the following. You can take the surface defect, which now lives in x and t space at y equals z equals 0, and you can take one of these line defects and put it embed it inside the surface defect. And so that implies that you get framed BPS states for interfaces in 1 plus 1 dimensional models. And actually, that's something that Davide and Edward and I spent a lot of time understanding. And Asan Khan and I have made some interesting progress on understanding further. OK, so let's move on. So that's just a quick overview of the different kinds of new BPS states you get. And they have new indices and new Wallcrossing formulas. So it's a very, very rich story. Now, let's go back now to pure 4-dimensional theory. And I want to talk a little bit about hyperkahler geometry, which again is where my project with Andy and Davide started. And so this begins by taking a 4-dimensional theory and you compactify it on 3-dimensional Minkowski space times a circle of radius r. And so now what's the low energy effective theory? The low energy effective theory now is going to be a sigma model where with target the moduli space of 3-dimensional vacua, of course. And that moduli space of 3-dimensional vacua is going to be a bundle over the Coulomb branch, where above a generic point u on the Coulomb branch, I'm going to have a torus. So this is a torus. And what is this torus? Well, what new boundary conditions do you need to specify when you compactify the theory on a circle? Well, one thing you have that you didn't have before is you have holonomy of the gauge field. This is the low energy abelian gauge field. You have holonomy of that gauge field around that circle. That in general is a function of x, but now we want to specify a boundary condition on its limit as x goes to infinity. And I'll call that theta electric, and of course that's a periodic value of a variable. And the other thing you can do is the gauge field in 3 dimensions can be dualized to a periodic scalar, theta m of x. And so we have another set of periodic variables where we take the limit as x goes to infinity of theta m of x. Okay, so this torus is a Poisson torus in general, where we have theta m and theta electric once we've chosen some duality for him. That's what TU looks like. And yeah, so M is the moduli space of vacua. So this is now I'm describing a paper of Zyberg and Witten from '96, where they said this. They said that M is the space of vacua of the 3-dimensional low-energy effective theory, and because it has n equals 4 supersymmetry, that means it has a hyperkahler metric. All right, so turns out you can describe that hyperkahler metric rather explicitly, and that's where I'm headed. Now, a good way to get at that is to go back to these line defects. Now we've got these line defects. We've got a circle. We could wrap the line defects around the circle. So let's do that. So, so we take a line defect, preserving the supersymmetries characterized by zeta, and we wrap it around the circle. We calculate the path integral with these boundary conditions with a point u and theta as your boundary conditions at infinity. And so this becomes a function of u and theta. And so what GMN argue is that that can be decomposed over our charge sectors of these protected spin characters. And here I've taken y equals -1. I'll soon release that. Times some functions, y sub gamma L of u, theta, and zeta. OK? Now, now I just argued that this has Wallcrossing. And then we argue in our paper that this has no Wallcrossing, essentially because we've got an operator which is well defined in the UV. So if this has no Wallcrossing and this has Wallcrossing, this must change discontinuously across k-walls. OK, so what's the change? Well, by thinking about the halo picture, OK, so I erased it, but there's this halo picture for the states that come and go. So you think carefully about the halo picture and how what that says about the variation of this omega, and you deduce that y sub gamma L goes to 1 plus sigma gamma y gamma. So Edward told me he had to leave early. It's not a protest, in case you're wondering. OK, what happens is you get this formula here, y gamma L. And so that's equal to something we call k sub L to the omega of gamma on y sub gamma L. We call that a KS transformation, Kontsevich-Sleivelman transformation. And those of you who like cluster coordinates and things like that will recognize that this is very close to a cluster transformation. So the only difference is that sigma gamma can either be +1 or -1, depending on whether your 4-dimensional BPS state is a vector multiplet or a hypermultiplet. OK, so it's a cluster-like transformation. And so you deduce this rather directly from this halo picture, these Fock spaces that come and go. Now, the other thing you could do is you could take a semi-classical limit. You can take r goes to infinity, and u goes to infinity. It's not really necessary to take u goes to infinity, but certainly you should take r goes to infinity. And then what you deduce is that this thing is asymptotic to r z gamma over zeta plus I theta dot gamma plus r zeta z gamma bar. And I'll call this y gamma semi-flat. Okay, so we have a kind of discontinuity across the k-walls, and we have a boundary condition, and so this implies a Riemann-Hilbert problem, and you solve the Riemann-Hilbert problem by an integral equation. So now you can deduce what these y gammas are, at least a very useful equation that they satisfy. And I better leave myself some space for that. Let me try and squeeze it in here. Log y gamma of u, theta, and zeta is equal to log of y gamma semi-flat of u, theta, and zeta plus the sum over all gamma prime of the ordinary BPS degeneracies, that's really important, times the integral from minus infinity to infinity d rho prime, some explicitly known kernel, times log of 1 plus sigma gamma prime y gamma prime of u, theta, and zeta prime equals e to the I alpha gamma prime minus rho prime, where z gamma prime has phase e to the I alpha gamma prime. All right. So there's an integral equation for you. If you look at the appropriate phase of zeta, then this thing is going to be exponentially decaying as you go out to r goes to infinity. So this is going to go like exponential minus r times the absolute value of z gamma along a suitable ray in the zeta plane. Okay, so you should think of this as exponentially decaying. Okay, so you can iterate this, this integral equation, and it converges very fast, exponentially fast. So it's very good for determining these functions. Mm-hmm.
So this equation is looks like a TVA equation.
That's one of my remarks. Yep. But I can't say much more than that. I wish I could. So, so now let me make a few remarks about this, this integral equation. So the first remark is that the y gamma allow the construction of the hyperkahler of Zyberg and Witten's hyperkahler on M. And why is that? Because we argue that they're what are called twister coordinates, which just means that if we choose a basis, gamma I is a basis for gamma u, then we can write d log of y gamma I wedge d log of y gamma j. They're both twister and cluster coordinates. So they're really good coordinates. We love them. We call them Darboux functions. And so you take this expression. So this is a certain 2 form. And we argue that, so these are functions of zeta, as u and theta. And we argue that this has a 3-term expansion in zeta. And so that allows us to pull off the 0, the 2, 0, the 1, 1, and the 0, 2 forms. And knowing those 3 forms, you got your hyperkahler metric. And then the metric is continuous across the marginal stability wall of gamma 1 and gamma 2 because of the Kontsevich-Soibam and Wallcrossing formula. This is not the best way to think about it. This is our first derivation of the Kontsevich-Soibam and Wallcrossing formula, but it's a correct derivation. So you see, these degeneracies are jumping across walls of marginal stability, So this integral equation is changing in complicated ways, and you would think, uh-oh, that's going to make this metric that I'm deriving discontinuous. And the magic of the KS Wallcrossing formula is that, in fact, it's a continuous metric. The next remark was just made by someone in the audience, is that this looks extremely similar to Zamolodchikov's thermodynamic beta ansatz. It's formally identical, and I don't think anybody has given any convincing explanation why that is so. The next remark is that there exist similar statements for 2D 4D systems, and that leads to integral equations with which you can actually explicitly solve Hitchin's equations, and I'll just leave that, and construct hyperholomorphic vector bundles. And finally, we can generalize to y not equal to -1. So you see, here I put y equals -1. I am talking about honest-to-God functions on the Seiberg-Witten moduli space. But now we can also generalize to y equals general. And that takes us into non-commutative geometry. So that brings me to topic 6. And I'm over time. Well, I need some direction from the chair who's bored.
For the next punchline, there's so many punchlines.
Yeah. Number 6 is how much time? I got 3 pages of notes. I would guesstimate 6, 7 minutes, unless you ask a hard question.
To the end, you're not at the half.
What?
You've done 5 out of 11, so it's not even a half.
Well, I didn't tell you what weighting there is.
Since I don't know, I assume it's equal.
Well, that's wrong. It's not homogeneous. No, 6 is the maximum we're going to do. So the question is, do you want to hear 6 or not?
I definitely want, but the question is, given that there are weights, it's not 1/5 of the time we spent so far, or is it?
I just told you it's 3 pages of notes, which turns into around 6 minutes. Go for it.
Then we can start
Okay.
negotiating.
Let's see if I'm right. So it's 250. Okay, here we go. So what we do is we introduce so let me finish the title, the derivation of the Kontsevich-Soyevon Wallcrossing formula. So we introduce what's called a formal line defect, where what we do is we take a sum over this lattice of, or this torsor for the lattice of charges associated with our line operator, and we have omega of L zeta, gamma L, y, and u, and now we put a non-commutative variable here. So these satisfy a non-commutative torus algebra. This looks like it's just coming out of the blue, but it's actually very closely related to those Fock spaces I was talking about. So again, as we cross the K-wall, W of gamma, if you take that Fock space picture seriously, you can say exactly how these are changing. They're changing by Fock spaces coming and going. And you derive a formula that looks like this. F of L zeta goes to K of gamma, F of L zeta, K of gamma inverse. And this K of gamma, this conjugation by K of gamma, takes into account the creation and annihilation of these Fock spaces of BPS particles. For example, if remember this, let me remind you, this K-wall is U of zeta such that, zeta inverse Z gamma is less than 0, and I'm not sure I wrote this before, so let me write it now. BPS gamma U is not the 0 vector space. I think in my haste I forgot to write that second condition. Now, for example, if BPS gamma U is only hypermultiplets, then this K of gamma, what is this K of gamma? This K of gamma is what's called the quantum dilogarithm, which sounds very scary. It's a certain infinite product. Although, well, okay, it's an infinite product. No way of getting around that. But it's not so scary because, you see, what happens, you have this simple Heisenberg algebra, you do this conjugation, and what you get are just Fox-based characters. It's sort of guaranteed. It's engineered to produce Fox-based characters multiplying this omega. And so now that's all we need. So now I can tell you what the Kontsevich, Coulomb, and Wallcrossing formula is, and that would be a good place to end. So now we can derive the Kontsevich, Coulomb, and Wallcrossing formula. Okay, so here we are in the U-plane. And here's the marginal stability wall for gamma 1 and gamma 2. Okay, and so there are some BPS degeneracies, omega minus on this side and omega plus on this side, okay? And they change. And the Kontsevich, Coulomb, and Wallcrossing formula tells us how omega plus changes to omega minus as we go across the wall. Now, let's think about one of these BPS walls. Say W gamma 2. Well, these are both real codimension 1 subvarieties of the U-plane, of the Coulomb branch. So they intersect in codimension 2 subvariety. Okay? So what is this is where Z of gamma 1 is parallel to Z of gamma 2, and this is where Z of gamma 2 is parallel to minus zeta. So if I have 3 lines in a plane, in general they do not intersect, but because of this, because of the conditions here, they do in this case, because this is where Z of gamma 1 is parallel to minus zeta. Right? So if these are parallel and these are parallel, then those are parallel. Okay? So they intersect in this same codimension 2. And not only that, if I take any positive linear combination, n1 gamma 1 plus n2 gamma 2, because of the linearity of the central charge that I mentioned before, so if n1 and n2 are positive, not negative, then these walls are all intersecting in this one codimension 2. So we could just think we're working in the plane, and we have, in principle, infinitely many walls, depending on whether those spaces are 0 or not. OK, so now let's take a point over here. Actually, this is U in zeta space. So let's take a point over here, U in zeta 1, and a point over here, U in zeta 2. And do you have colored chalk? Yes. And let's choose a path. P1 here and P2 here. And let's ask how this F changes as we go along P1 and P2. So along P1, well, F of 2 is a product of all these K operations times F of 1, K of P1 inverse. And along P2, F of 2 is this K operation along the path P2, F of 2, K of P2 inverse. Well, what is K of P1? So K of P1, well, as you cross these different walls, you have a K transformation each time you cross a K wall. OK, so you have, so the first one you get is this wall. That's the wall W of gamma 1. So you get K of gamma 1. And then you get, in principle, infinitely many walls. And you finish, this is the last wall you go through, K of gamma 2. And these are computed using omega minus. You see, K depends on omega. And so you're only using the omega minuses on the left side of this wall. Whereas for K of P2, you have K of gamma 2. Because you see, you cross this K gamma 2 wall first, and then a lot of walls, and then you end up with K of gamma 1. And here, you're using omega plus. But you see, f of 2 is f of 2, and f of, whoops, that's wrong. F of 1 is f of 1. And so we should have k of p1 equals k of p2. And that is the Kontsevich, Schleibelman, Wallcrossing formula. That's exactly what it is. Yes, Shuheng, what's?
Why is minus 1? The Wallcrossing formula is derived by demanding a physical quantity, namely the hyperkahler metric,
Mhm.
where the 3D theory is
Mhm.
continuous.
Mhm.
But why is not minus 1, namely the proof you are presenting here,
Mhm.
seems to be demanding this f of ls, this to be single value. But what's the...
Well, f is single value. There's no question about that. It's defined at a point.
Well, what's the physical interpretation for f of ls?
Well, I'm not quite sure how to answer that question. I mean, there are many. Let's see. By the way, did I win my bet with Nadi? I lost it. It's 2:58. 2 minutes too long. Sorry. So yeah, to answer your question. Well, I'm not quite sure how to answer that question. There are many derivations of the Kontsevich-Schleibelman Wallcrossing formula, for example. Cicciotti and Vafa have things involving geometric engineering and M5 brains and all sorts of
But
stuff.
for this derivation, you
Yeah.
just presented the star is this f of ls, which involves some non-commutative variable.
Yes,
Is there
yes.
a nice physical way to think about it?
Oh, yes, there is. And that was the point of this talk, and therefore I have failed in my communication abilities. The point of this talk is that halo picture, is a nice physical picture of exactly what's going on in the KS Wallcrossing formula. As you cross these walls, various Fock spaces come and go, okay, in ways that I sketched. And it's these, I mean, we're never going to, we're not going to get to categorification of Wallcrossing formula. But the dream, still an open problem, but the dream is to make good mathematical sense of a mathematical operation of a creation and annihilation of Fock spaces. And so the idea is that you create and annihilate Fock spaces this way and this way. They depend on different BPS degeneracies, but somehow the product of these creation and annihilation operators is the same. So to me, that's a very physical picture, these Fock spaces of halo particles coming and going.
But more specifically, what does X gamma mean physically?
Yeah, that's a good question. So, again, that's a kind of an open-ended question. So one interpretation is the following. So this is a, okay, so M, our hyperkahler manifold, being hyperkahler, has lots of complex structures. So in the complex structure zeta, it's, if I specify a zeta, I can use that as a point on the twistor sphere to specify a complex structure. On M zeta as a complex manifold, these are holomorphic functions. And in fact, if I look at all the various line operators, line defects, I get all the holomorphic functions. I get the full ring of holomorphic functions. What am I doing here? I'm quantizing the holomorphic functions. Okay, so I think of these X gammas as quantizations of the Y gammas in a deformation quantization of the moduli space, of the hyperkahler moduli space. It's a holomorphic symplectic manifold. I can quantize it. These are the deformations. So you can also try and interpret these Y gammas. So these Y gammas are quantizing to these X gammas. You can think of these as vebs of infrared line defects, if you want to try and think of it that way. And so again, these are sort of infrared, somehow non-commutative operators associated with those infrared defects. So I'm sure there are better answers, but that's an answer. All right, sorry to go over time.